Continuing with this tutorial, now is the turn for the square root function. In the square root function, usually we get a graph like this we have here. In this example, we have the function of x square root of x minus 3. So it starts in plus 3 in the x-axis, and we will notice that according to the number we have after the x, it moves to the right or to the left of x-axis. Interpreting this graph, we can find the domain and the range. The domain starts in 3 until infinite. Now, the range starts in 0 until infinite. So we go here. The domain is 3, infinite. And what about the range? As I told you, it starts in 0 and goes until infinite. The domain and the range of this function. Another example. Fx equals the square root of 3 plus 3. Observe the previous one. The previous one was minus 3 and it started in plus 3 in the x-axis. This is plus 3 and it starts in minus 3 in the x-axis. So we're going to consult why it happens. Why the number after the x determines the initial position in x-axis. Okay, the domain of this function, the domain starts in minus 3 and goes until infinite. So negative 3, infinite. That's the domain. What about the range? The range starts in 0. It starts in 0 and goes until infinite. The domain and the range of this other square root function. This one. F of x square root of 9 minus x squared. We get a semicircle. Why? We have two elements inside. 9 is a perfect square and x squared. When we have x squared, the square root of a number raised to the second power is the same number, you know. But it's a semicircle because inside we cannot have a negative number. So when we have a negative number, it's not possible to graph. That's why the graph of this is a semicircle. We don't have values here in the negative. We don't have values here in the negative part. And finally, rational functions. Rational functions. I've told you many times that a ration is the representation of P over Q, and Q can be 0. It can be 0 because it gives an indetermination, and it's necessary to determine the domain and the range of the function. And the asymptote. An asymptote, like I said here, is an imaginary line approached but never touched. So it's never touched by the graph of the function. It happens usually in the rational functions. Here we have an asymptote. Can you notice it? Here is an asymptote in the domain. In 0.5, here it's at minus 0.5x. And we have another asymptote in the range, is this one, in 2. So with this graph, we can infer that the domain goes from the domain minus infinite, open brackets, until minus 0.5, open brackets, union, open brackets, minus 0.5, comma, infinite, open, close, open brackets. Here we have another function, a rational function with two asymptotes. Look at them here. The first one, it determines the range, and this one determines the domain. So the domain is in -2. -2, observe here. It's imaginary, just to sign the place that is not touched by the graph. And the same thing happens here in the range. It's an imaginary line. So this graph extends until infinite, but it never touches 1. Okay, let's analyze this graph. Take your time and try to solve it. Okay. When you have this situation, the first thing you should do is to draw the asymptotes. This is the range, this is the domain. So it makes easier to interpret the graph. So I know that the domain doesn't touch 2 positive in x, and the range doesn't touch 3. Now we go here. The domain minus infinite, yeah, minus infinite, comma, 2. Both of them with open brackets. Okay, union, and here we have again 2 plus infinite. Perfect. Plus infinite. Domain. And what about the range? The range. So for the range, we take into account the y. It starts minus infinite and it goes up until 3. So here we have minus infinite, comma, 3, union, all of them with the round brackets, 3, comma, plus infinite. And here we have the domain and the range of the function. And finally we go to the simplification. The simplification is important. Why? Because sometimes we have a rational function, but after using the factorization case, we realize that it's not a rational function, it's a linear function. One example here, 1/2 multiplied by 6x plus 10 plus 3 multiplied by x minus 4. What we do here is to use the distributive property, so multiply 1/2 by 6x and then we multiply 1/2 by 10. Here we have the answer in this part. And then we multiply 3 by x and 3 by minus 4. Let's see. 3 multiplied by x, 3x. And 3 multiplied by minus 4, minus 12. And finally, what we do is to combine the like terms. 3x plus 3x, 6x. And then we have plus 5 minus 12, negative 7. So this is the answer. 6x minus 7. We can also evaluate the expression. To evaluate the expression is to solve it giving a value to x, to y, or to both of them. Here we've got 2x minus 3xy plus 4y, and we assign the value x, 3, and y minus 5. So what we do is to substitute, to replace x by 3, by here, and we replace y by minus 5, like here, and finally we do the operation. 2 times 3, 6, minus 3 times 3, 9, 9 times 5, 45, but negative multiplied by negative gives positive, plus positive multiplied by negative, negative, 4 times 5, 20. So here we've got 6 plus 45 equals 51, minus 20, 31. That is the final answer. The only thing we have to take here to bear in mind is the law of signs. Common mistakes, it happens when we raise a number to the second power. If the number is negative, any negative number raised to the second power is positive. Minus 3 multiplied by minus 3, 9 positive. Minus 2 multiplied by minus 2, 4 positive. Different if we have a negative sign before the x. Different because we have positive answer, but it changes because the sign is negative. So the answer here is minus 9, like this. But the answer here is 9, like this. This is the correct form to solve these two operations. Other case of factorization, and use it to simplify an expression when graphing a function. So here what we have to do is to match. So let's match 4 times y, 4y minus 8. Where is it here? Okay, this one, 3y plus 4, it gives 3y plus 12. 3y plus 12. Do you see it? You don't see it. 3y plus 12. So you have to write it here. 3y 3y plus 12. Okay, and you can practice completing this. Factorize each expression. Alright, so here common factor. We have the common factor, so we'll have to do this to match here the answer. Okay, the answer for this 2 times 5, 10, AB will be this one, yeah, and this one 6C. You complete the other two examples, these two examples, and finally here, so we need to analyze what case of factorization it is. It's not an identity, it's the case of ax squared plus bx plus c. And if you remember, in this case, what you have to do is to open two brackets, yeah, and to put the answer. So here we have x plus, and in the other one we put x, positive, 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 and then we need to find two numbers that multiply give 3 and added 4, yeah, and so on. The two numbers are 3 and 1. 3 times 1, 3, and 3 plus 1, 4, and the same thing with the others. So you solve these ones. Okay, that's all by now. I hope this other video was also useful. to graph two functions. And now I'm going to ask you a favor. For the next class, study composition functions. This is the topic for the next class. See you, have a great time.